So I recently obtained from eBay a Sencore LC103 capacitor and inductor analyzer, what many consider to be the gold standard of capacitor testers and inductors, but normally use it for capacitors. And I looked around and I did not see a teardown of one of these on YouTube anywhere. So I figured I'd do a quick YouTube video here, and I think I'm going to go handheld just because I don't have a macro lens or anything to get real close in. I don't want to go super in detail here. Just wanted to do a quick teardown of this thing, give you a sweep there. So we have our front board here with all of our buttons, and it looks like we have a Noritake VFD, vacuum fluorescent display, with a custom character chipset. This will be for the high voltage. There'll be a boost converter there, behind in there. And it's pretty bright, easy to read, so that's in good shape. And then we have our input, which comes from down in there, comes up over here. We've got a big resistor, that's probably for discharging the capacitors. A couple different relays, as you would expect to see. These are all relays here. So for various range switching, some of these are going to be, one of these will be to switch in the discharge of the capacitors. But yeah, stuff you would expect. This guy here or this guy there is probably your ADC. I'm not sure which one's the main ADC. I don't even know what the topology of this is exactly. But you've got all kinds of what I would suspect are op amps in here. All kinds of analog goodness all along in here. A transistor like this in a metal case. This was built in '97, I believe. I saw a date code on one of these chips. Oh, here on the EPROM. 1997 AMD. So this was built in '97. Probably one of the last major capacitor testers built by Sencore. I'm not sure if there's a more updated model. I don't think so. There's probably not a greater capacitor tester than this one out there on the market, to be honest. If there is, let me know. I'd be interested in that, but I think this is probably one of the best. Oh, here we've got a spark arrestor, spark gap in there in case a capacitor were to have too much voltage on it when you connect it. So there's a good amount of front-end protection. It's interesting they decided here they didn't need that relay, so they jumpered it out. And we've got a good share of bodge wires in here. Got one here for the resistor. We've got a resistor bodged across there. I don't think they made a whole lot of these things, so it makes more sense to do things like that. And we got a little cap going across there. It makes more sense to do that than to completely respin it. So I'm not going to pretend I know exactly what everything is going on here. Some kind of transistor package there. Couldn't be bothered to take that apart. You could tell that these are important. You wouldn't have capacitors, film capacitors of this type, unless they were doing some type of important timing function. Probably, I would guess, some type of multi-slope or dual slope integration. Although I'm thinking that the ADC is somewhere over here, but I don't see any capacitors that would make sense over there. So maybe that. I can't see the numbers on these chips. Maybe one of these is actually, that's not in there. Those are going to be op amps. Maybe that's an ADC. Can you read it? I can't read it. Or perhaps one of these two. I'm not sure. Sorry it's so shaky. I really just could not be bothered to do this right. Looks like we've got memory probably here, and here, and here. Then we have a Xilinx. That's probably going to be an FPGA. I don't think it's a CPLD or anything like that. It looks like here, what is this, maybe SRAM or SDRAM? Here, this guy, that's probably a programming sticker. You see what that is? 17128 EPC. Is that a PROM? I think it's just a programmable read-only memory, like with actual fuses in it, rather than a EEPROM or anything like that. The thing I actually took this apart for is this guy, E² PROM, or I suspect is an E² PROM. I don't think there's actually a UV window under there, but maybe there is. I can't tell. We'll get that sticker off and find out. But my concern is this unit, you can see the date there, let me turn it so you can see it, 1997, this thing is now 24 years old, and the average life expectancy of an IC like this is 20 years. So it's getting to a point where whatever special Sencore Inc. magic is in this chip, we don't want to lose that. So what I want to do is actually read the data off of that and save a copy to my computer. And I'll probably do the same with this EPROM over here as well, if I can read it, just so I have a copy of it. And if we ever have to, if it fails, then we could just burn a new chip. And I'll show you my programmer and how all that's done. But I don't want to lose this sticker. Good enough. I'm going to flip this over here, and it's very light. It is extremely light. This whole unit, you would not expect it to be this light, but you know, there's no major transformers in here, no big heavy linear transformers, so it looks like all of this is part of a switch mode power supply. You've got to have your high voltage supply in here because you can program 0 to 1000 volts for DC leakage testing on capacitors. So that's all power supply stuff there. I don't know, hopefully you can see these chips, what they are there, because I can't. Not through the viewfinder anyway. My battery's gonna die. May cut out on me here. So there's that. Big 1% resistor there. Oh well, that's interesting. TO247 package, big guy there. Not sure what that is. Probably some kind of FET. All top quality capacitors. These are Nichicons. It looks like they've been pretty consistent with the Nichicons. Is this one a Nichicon? What is that one? I don't know. It says Japan. Anyway. Yeah, pretty high quality stuff in here, as you would expect from Sencore. But the thing I'm mostly interested in is that EPROM for now. Oh, and there's a battery compartment in the back. You can open that up. There's a NiCad battery that would go in there, but we don't want any part of that. Could come up with some kind of lithium-ion solution, but I don't really plan on traveling with this. So let me charge the battery on my camera and get the EPROM reader out, and we'll read this chip. Alright, so I've peeled the stickers back. I pulled this one off here. That one is the 17128 EPC. So that one is an EPROM. And then this one is, of course, an EPROM. I peeled the sticker back, but it's one of those foil types, so it actually just ripped. It sometimes happens, unfortunately. It looks like it's an AM27C010-150. So we'll have to check in the computer and see if that's one of the ones that my EPROM programmer can actually program. And let's take a little peekaboo under here, if we can, and see if this is the UV type. Oh, yep. So I don't really want to expose that hold on. Okay, so I have an example here. First I'll show you, this is my EPROM Programmer Mini Pro. It's a TL866 high performance. Yeah, okay. But yeah, so it's just basically you have a ZIF socket here. That's a ZIF, zero insertion force socket. You put the chip in here, it reads it, or you write to it, whichever the case may be. And when I say UV type, here's an example. So you can actually see, I don't know if I can zoom in or not. There we go. Can I hold it steady? You can actually see the dye in there. Not too far. You can actually see the dye and all the bond wires. And right now it's getting some ultraviolet light from the lap lights. Not much, but there's a small amount there, I'm sure. And that's why these stickers are actually over that, so that you don't expose that dye to ultraviolet light. Now, you'd have to expose it to for a very long time at that low level to actually erase it, and that is why you use one of these. Probably not one this cheap. This is comically cheap. I got it on eBay. It just says EPROM. And what you do is you put the chip in the tray like that, close it, and there's a ultraviolet light in there that will shine onto that die and actually erase all of the memory. So that's how you actually erase this type. I don't want to erase it, I want to read it, so I want to keep that sticker intact and put it in my programmer there and read the memory out of it. But the way these work is when it's programmed at the factory, they put a programming voltage on it that's usually higher, you know, something like 18-20 volts sometimes, and it will actually put a charge on FET transistors that are in there, and it just holds that charge for a very long time. They've got insulated gates, and it can hold that charge for a very long time. But that's why I said these may have only something like a 20-year service life to them. Now, they definitely can live a lot longer than that, but it's not really guaranteed after 20 years. So I can guarantee that this one works because I've tried it. But I don't want to take any more chances. I'm going to read this out and at least make sure I have the binary file in case I ever need to program it. So I'll take that one, and let's take a look at it. Okay, so we got to get this IC out of here for testing very carefully. Well, this is going to be tough to get this side here. If I bust a pin, it's going to be a lot harder to get the data out of this thing. I mean, I can always buy a new IC, but if I can't get the data out of it, then that's worthless. Just very carefully, very slowly. Ooh, it's nerve-wracking. Got it. So then you just drop the chip. It says that the little horseshoe on the end there goes this way. Clamp it in, and you come over here to the program. Sorry, I know this is crude. Should use screen capture. You can see here we have the chip already selected, AM27C010. It's an AMD chip. It's a DIP32 package. And come up to device. And let's just try read ID first. Look, it has an identification there, 010E. Let's do a full read. Okay, code memory. It is in the socket. And hit read. It took 2.2 seconds. Read finished. And there it is. Here's our data. So I'll just save this and oh, here, this is interesting. You can see the ASCII here for what it is. I can save this data, and then in the future, if this IC ever goes bad, then I could always just write a new one. It might not hurt to just reprogram the device with its own data, but I'm not gonna risk that right now because I don't know, something could go wrong. I'd rather program a blank device and that way at least still have a backup. But you can see here it says capacitor test in progress. Years are shorted. Out of range, cap value is out of range. ESR appears open. So these are different messages that it would put on the screen. Cap discharging, good, bad. Yeah, these are all messages that would end up going on the screen. It looks like they've programmed quite a bit of this chip. They used a lot of the actual program memory. Wow, it just keeps going. Amazing. Scroll down to the bottom here. That re-enter voltage. All these error messages. Wow. They used just about the entire chip. Wow. Just barely made it fit. So anyway, that's enough of that. We got the chip read. Wanted to show you how that works. I'm just going to go ahead and pop the chip back into the capacitor analyzer. I do want to go through and this configuration memory PROM here for the FPGA. I want to actually go ahead and see if I can get that out. Now, I can't desolder it and put it into my chip reader here because it's not actually in the list of supported devices. It's just a serial bit stream out, however, so I'm thinking I can put my logic analyzer on it and we can watch the bit stream come out and we could save that data, so at least then we would have the data that we would need to reprogram it with later if it were to ever fail. So I'll go ahead and set that up real quick and we'll take a look at that. Okay, so here's the setup. We have the FPGA here. This looks like that's a JTAG header that's unpopulated. All the traces are going between there. And here's that configuration memory. So because a FPGA is basically dumb, when you first install it, it's completely dumb. It's just a collection of gates, and it needs to be programmed in either Verilog or VHDL in order to actually have it do anything. There's probably a soft processor in here, a little microcontroller that is doing a little bit of the basic control, especially to send out the clock pulses to this configuration memory and get all of the gates set up in their proper orientation. So when we power it on, when we power it on, all of the data should be captured on our logic analyzer, and what do we have here? The data. So here's our bit stream, and here's the clock. So this is the clock pulses that's coming from the FPGA, and this is the chip enable, which incidentally never starts out high. I tried even nanoseconds after the thing's powered on, and it never goes high. So it just stays low, and then it goes high after the data's been transferred. That's a little unusual. I thought it would be more like a SPI protocol, but it is not. So it actually, my software was not working to do SPI decoding on this with the chip select enabled, so I have to actually disable that from decoding But once I do that, we can load up the hex view and you can see all of the data. So this is what we actually get. And if you look back at the data here, sorry, this is crude. I always apologize for it being crude, and then I just don't care and do it this way anyway. So you can see, of course I zoom in on a blank section there and go to the right here, find something interesting. You can kind of see all that data in there. These are all your various clock pulses, and this is the actual data. You can see that the data is overlaid. I have it in binary right now, laid over the data signals there. And it looks like our clock frequency is, you can't see it down there. You probably still can't see it because of glare, but that says 1.1 megahertz. I could bring this down and do it right, I suppose. So there we go, 1.1 megahertz. Time low, time high, so it's about 450 nanoseconds each. So yeah, roughly 50% duty cycle. There you have it. There's our serial data that came out of it. Pretty confident that I've collected all of it. So if I zoom out, there's all of that data, and I'll just export the packets wasn't what I wanted actually. You'll see it'll just show a different view. It just shows individual packets here on the MISO line, master and slave out. But I can export that as a text file, and that'll have all the data, so I can save that. And I've seen on the EEV blog forum that a lot of people actually did capture this EPROM data. But that's really not that useful. It's only useful for your instrument. A lot of people have posted it online, but it's got calibration constants on it. So I guess if you were really in dire straits and you have bricked it because this failed, or you ruined it by playing with it, whatever the case may be, you could get it close. You could at least get it back up and running, although your calibration would be useless, and these are not easy to calibrate, so you really don't want to run into that situation because you need special software that you can't get anymore. You need test equipment that is very specialized and difficult, and Sencore does not have that equipment. They've long since dissolved this branch of their company, so unfortunately there is no calibrating this thing. It's either going to be close or not, and there's nothing you can do about it. But I figure having this image plus the FPGA configuration memory, those are the two types of memory that we have here, at least that would get us going, so I have that as a backup. Anyway, I think this video is long enough. I had to use this other laptop here. This isn't my typical laptop because the charger for my other laptop that I have here failed. I have lots of laptops, so that's not a problem, but that might be my next video, is just figuring out what's going on with that charger and actually fixing it. So anyway, I hope you thought that was interesting, maybe to help you, even if you just wanted to see a teardown of one of these things. I didn't think there's any other videos out there on YouTube, so hope you enjoyed that.